Okay, this short video is aimed to support Unit 28, Assignment 5, Task number 5, which is where we're asked to use integration to find the average value of a waveform, which is something that's common to do in electronics and things like that. You're asked to find the average voltage of a function like this. Before we do this, though, I want to just show how the process is arrived at. Why is the average value given by this function? And then you can go ahead and carry out the task. If we look at any function, this process of finding the average value works for any function, ft for example, so any function. In this particular case, a function has this sort of curve, so it varies with time, so time on the x-axis here. If we think about what the average value means, it means some sort of number which represents the function over a period of time, in this case 10 seconds, say. So you'd expect it, as this dotted line shows, to fall somewhere in the middle of the curve like that. And it forms a rectangle. If we think about, if we actually have the average value, that would form a rectangle, which would have the same area as the integral underneath this curve, because the average value represents the function. So if I find the integral between the limits 0 and 10 for the whole function, that value for the area, if the average value is correct, should give me the same area as this rectangle. And that's the key to the process. This rectangle area here should be the same as the area under the whole curve, if I've done it correctly. So we take that idea to allow us to find the average value. If I integrate under the curve and get the whole area under the curve here, and then divide that by this distance here, the width of the curve, then I'm going to get the average value, this value here, because that length from there to there multiplied by this length from here to here gives me the area of this rectangle. I hope that logic makes sense there. So in other words, to find the average value, we integrate across an interval, in this case between 0 and 10, or it could be between x1 or t1 in this case and t2. Integrate between limits to get the whole area under the curve, and then divide the answer by that interval, t2 minus t1 in this case, say, and that will give us the average value. And that's the process. You can use integration to find the average value for a function, and to do that we integrate between two limits, x1 and x2, or t1 and t2, and then divide the answer by the difference between those limits, t2 minus t1 or x2 minus x1, something like that. Written algebraically, it would look like this. f bar x, and remember, in statistics, x bar represented the average value, so for exactly the same reason we use fx bar to represent the average value for the function. So the average value of the function equals the integral between the limits, x2 and x1 in this case, of the function, divided by the width of the integral. Instead of dividing by x2 minus x1, we could multiply by 1 over x2 minus x1, which is this form of the equation here. So the average value is given by this, and that's the way you usually see it written in the textbook. But 1 over x2 minus x1 times the integral across that interval. So let's apply this formula. This is the formula that you need to use to find the average value of any function. And let's look at an example where we find the average value of a wave function like this. Vt equals 3 sine 100 pi t. So we want to find the average value over half a cycle. Half a cycle. So I've plotted it on autograph, and here's half a cycle. So what's the average value over that period of time? Well, we'd expect it to be somewhere here. And so what I'm going to do is integrate to get the area underneath the curve, the whole curve between the limits. And that should equal the same area as a rectangle, with that height being the average value, so we can then find the average value. Okay, as a little side issue, you might want to consider, what's this time here, 0.02? We talked about this thing before, but can you verify that that's 0.02 by looking at this? Remember what the 100 pi represents? Omega, the angular velocity, and omega equals 2 pi f. So we can come up with a value for the frequency, and the period of the wave is 1 over the frequency, and this is the period here. So as a little extension question, we could verify that this wave function has a period of 0.02 seconds. However, let's just look at it and then find the average value for this function. So we're going to average this over half a cycle between 0 and 0.01. So we write down the average value of the function is 1 over 0.01 minus 0 times the integral between 0.01 and 0 of the function. So what we've got to do now is integrate the function and work out the value. So this equals, well, 1 over 0.01 is 100. Integral between 0 and 0.01 of 3 sine 100 pi t with respect to t. Performing the integration from standard integrals, you should remember that the sine becomes minus cosine and the 100 pi comes out and goes underneath. So we end up with, this equals 100 times minus 3 over 100 pi cosine 100 pi t between 0 and 0.01. The minus 3 over 100 pi can come outside the bracket because that's a constant. Hundreds cancel, so we're left with minus 3 over pi times the cosine of 100 pi t between 0 and 0.01. So putting in the limits, we get minus 3 over pi, and then using curly brackets, it'll be the cosine of 100 pi times 0.01, which turns out to be pi, minus the cosine of 0. You can use a calculator to work out the cosine of pi and the cosine of 0, but hopefully you don't need a calculator, because if we just quickly sketch the cosine curve across one cycle, that's 2 pi, one complete revolution. So this is pi. So what's the cosine of pi? Minus 1. What's the cosine of 0? 1. So, in other words, the cosine of pi is minus 1 and the cosine of 0 is 1. So that means that the average value for the function, which is what this is telling us, remember, the average value of the function, voltage, average voltage, equals minus 3 over pi times minus 1 is minus 2. So this equals 6 over pi. So the average value for the voltage is 6 over pi. We can leave it like that because that's an exact answer, or we can get our calculator out and give ourselves a value to an appropriate number of significant figures. Now you can go back and try the task 5, and evaluate an average value for the function correct to 3 significant figures.